In this video, we're going to be giving an introduction to elimination reactions. So we saw in chapter 6 that one type of reaction that we learned in this class is nucleophilic substitution reactions. And this is a very essential technique used in organic chemistry labs to substitute one functional group for another. As we'll see in this chapter, elimination reactions are a very good technique for the preparation of alkenes. So in general, we'll look at the general reactivity of an elimination reaction. So here we just have two adjacent carbons next to one another. We'll call this the alpha carbon and we'll call this the beta carbon. In general, what happens in the elimination reaction is we'll lose AB and we'll be left with an alkene in its place. Since we are losing AB together, where A is the alpha and B is the beta, this is sometimes called a beta elimination. Or since they are 1-2 to one another, 1-2 positions, this is sometimes called a 1-2 elimination. So beta elimination, 1-2 elimination, elimination reactions. All of these are going to be turning a disubstituted alkane into an alkene. So there's a couple different kinds of elimination reactions that we see in this course. One of them is going to be a dehydrogenation. So we'll take this basic form of C and these lines just mean there are substituents on them. They could be anything. In the dehydrogenation, those two substituents are going to be HH. And actually, let me make those different color. Actually, in this case, we'll leave them the same color. In future ones, we'll make them different colors. So we lose HH. In this reaction, this is usually done at very high heat, usually 750 to 1,000 degrees. Sometimes there's a catalyst, but what we do is we're left with the alkene, and we lose an equivalent of H2. So we've lost hydrogen. We've coupled H and H to lose H2. This is not a very practical reaction in the lab, mainly because, this requires temperatures of around 750 degrees Celsius or higher. So usually when you're heating things that high, you're destroying other functionality in the molecule. So this is not very practical. And also, we can't really achieve these temperatures in a research lab or in a teaching lab. So this is not a very practical reaction. This is done on an industrial scale. Another common reaction, and this is one we will see in this chapter, is dehydration. So in a dehydration reaction, we'll start with the same form. On one carbon, we have an H. On the other carbon, we have an OH, so we have an alcohol. Upon addition of acid, and I'll just write H plus for this case, and heat, we are left with the alkene, same as before. And in this reaction, we've coupled H and OH, and if you do the math, you'll see that this is just water, so this is just H2O. So you lose water. This is why it's called a dehydration. You've lost water, and you've generated an alkene. This is usually done with an acid catalyst. So catalyst meaning you only need small amounts of it, usually H2SO4 or H3PO4. And there's usually ways to remove the water in the reaction as it proceeds. So dehydration is another very common reaction that we'll see in this class to prepare alkenes. And we'll examine the mechanism for these in later videos. The other one that we'll see in this chapter is called dehydrohalogenation. So in a dehydrohalogenation, again, start the same way, same form. We have an alkane. We have a hydrogen on one carbon, and then we'll have some kind of halogen, so that it's a Cl, a Br, an I, an F. And what is going to happen is, if you can imagine, we're coupling these two, we're coupling the H and X. This is done as the opposite of dehydration. This is done with base and usually heat. What we see in this reaction is we end up with the alkene. And then we've coupled H and X, we end up with an equivalent of HX, which is usually soaked up by the base. So we generate a mineral acid and an alkene. This requires strong base in order to make this happen. And depending on the alkane, it can be stronger or weaker. Strong bases like this include things like methoxide, ethoxide, terbutoxide, and all of these are going to have, or hydroxide, all of these will have metal counterions, so like sodium methoxide, potassium terbutoxide, barium hydroxide. All of these are going to be strong bases that can be used in the reaction of dehydrohalogenation. So again, we couple the two atoms that are next to each other, we lose an equivalent of hydrogen, we lose an equivalent of water, we lose an equivalent of HX, and we generate the alkene in the process. So we always are generating the alkene, and as we see, elimination reactions are going to be used to generate alkenes. It's a very useful reaction for generating alkenes in the lab. So we run into a number of issues about regioselectivity and stereoselectivity in doing elimination reactions. So say we're doing a, we have this kind of alcohol, and we want to add H2SO4. So we're doing a dehydration reaction and heat. So as we know, dehydration reactions will lose water and an equivalent of alkene, but you'll notice that there's two different places we can lose a hydrogen. We can lose this hydrogen in red. We can also lose this hydrogen in blue. So let's look at both of those products. So let's look at the red. So the red, if we lose the terminal hydrogen, we would end up with this alkene here, plus water. So we'd form the terminal alkene. If we lose the internal hydrogen, we would end up with the internal alkene. And this could be cis or trans, plus water. And the question is, which one of these is going to primarily form? And what we see is that this group of alkenes will primarily form over the monosubstitute alkene. And what this is called is, this is governed by what is known as Zaitsev's rule. So Zaitsev's rule is dictates that in elimination reactions, you form the more substituted alkene. So what we see is, since in this case we have a monosubstituted alkene, whereas if we do the internal elimination, we have the disubstituted alkene. So the disubstituted alkene is going to be preferred over the monosubstituted alkene because Zaitsev's rule dictates that the more substituted alkene is going to form in an elimination reaction. Moving even further, we have a question that says, between cis and trans, which one of these forms? So this is so Zaitsev's rule dictates regioselectivity, meaning that if we can have the mono or the disubstitute alkene, we're going to favor the di. We also have stereoselectivity, so which one are we going to favor, cis or trans? And if we remember from the previous video, that trans alkenes are going to be more stable than cis alkenes. So what we see is that this trans internal alkene is going to be formed primarily. It's going to be the major product, followed by the cis internal alkene, followed by the mono alkene. In reality, you probably end up with a mixture of these three alkenes, and you have to separate them out. But depending on the driving forces, how favorable it is to form the internal trans alkene, this might be 80%, this might be 95%, this might be 99%. Depending on how particularly stable this is. So we're always going to prefer the more substitute alkene, and we're going to prefer the trans isomer if we can form it. So just as a sample reaction, let's look at this dehydration. So I'll leave you if you want to pause this video and predict the product of this reaction. So once again, we have two options. We can abstract this hydrogen, or we can abstract this hydrogen in blue. If we abstract this hydrogen in blue, we're going to form the disubstituted alkene. If we abstract the hydrogen in red, we're going to form a trisubstituted alkene. Zaitsev's rule dictates where we want to form the more substituted product, so we will overwhelmingly form the trisubstituted product plus an equivalent of water to balance out that equation.